This chapter will focus on capacitors, which are going to be the first circuit component that we discuss. So the basics of capacitors is they're going to be a first step towards understanding how electronic circuits work and the different components that go into them. They're going to be a device. A capacitor is going to be a device that stores charge, and you can think of it as a very temporary battery. They're often very short-term storage of charge in different circuits. We'll combine them often with components in more complex circuits to, for example, filter signals in RF or microwave receivers to pick up only certain frequencies and not the whole spectrum of frequencies coming at you. So they'll be key to how antennae work in cell phones or in a car radio. The example we've seen a few times of two parallel large conducting plates are going to be a basic example of a capacitor. So what are capacitors and what's capacitance, and what's the basic introduction to this? So capacitors can be thought of as something that temporarily stores electric charge. Since work is done to put charge somewhere, if I'm going to put a whole bunch of positive charges in the same vicinity of each other, they're going to repel each other. I have to do work. And so in addition to storing charge, I can think of capacitors as storing energy because of the energy required to put charge on them to begin with. Generally, they'll consist of two different conductors because I want to be able to put charge onto them easily and then take the charge off of them easily. Conductors satisfy that requirement. We'll usually call them capacitor plates because it's easiest to think, as we'll see the first example we do, of two large parallel conducting plates. These will be separated by either vacuum or air, which is very close to vacuum in terms of the electrical properties, or they could be separated by an insulator called a dielectric, which will modify the properties of the capacitor. And as we'll see, for a given voltage, for a given battery we hook up to put charge onto the capacitors, we can often get more charge stored per volt if we fill it with a dielectric. So common capacitors are filled with dielectrics. And what you see here is the simplest example of a capacitor with air between it, two large flat plates. But these plates don't have to be large planes like that. They could be one inner plate here, another plate here rolled up, and then in between them, in that gap also rolled up, is an insulator. So capacitors just consist of two conducting surfaces with some gap between them that may or may not be filled with an insulator. Now, from the practical standpoint of engineering a circuit, we generally want to talk about applying a voltage to a capacitor, which is going to put charge on either plate of the capacitor and store it there temporarily. And so we're going to want to know how many coulombs of charge we get per volt we apply to the capacitor. And so capacitance is going to be a quantity defined for a given capacitor, which tells us the ratio of the charge that gets stored on the capacitor to the voltage we apply to the capacitor. And as you see here, here's an example of a certain voltage from a battery, putting charge plus Q and minus Q on that capacitor. The SI unit of capacitance, rather than writing coulomb per volt, which would be charge per volt, we're going to have a shorthand for that and call it the farad, 1F, named after Michael Faraday. A single farad ends up being very large. We'll see an example of this later on. So usually in practical capacitors for circuits, you're dealing with millifarads or lower. So how will our capacitance calculations work before we get into actually doing some core examples? So to calculate capacitance for a given configuration of conducting plates or sheets of some shape or another, we're going to assume, we're going to draw our capacitor, this geometry, assume that we put charge Q on it, meaning on one plate we put plus Q charge, on the other plate we put minus Q charge. We're going to determine the electric field between these conductors with those charges in place using some method, typically Gauss's law, but you could, in an advanced situation, use a different method or even numerical calculations on a computer if you're engineering a complex shape for your capacitor. And then using the electric field, we're going to find the voltage between the two plates. So now we have a thought experiment of putting a charge Q. We know the voltage between the two plates. Capacitance is defined as the ratio of that charge Q we put there to the voltage, and that will get us to capacitance. So in the next sections of videos, we're going to go through this calculation using Gauss's law to get the field and then the voltage from that for geometries where we can use Gauss's law, so planes, spheres, and cylinders, and see what this calculation results in.